through all this. So kind of like yesterday, we want to I'll make sure you see the stuff that we need to see. All right, so what I mentioned before is this is all review today, but it's things that you need to know pretty well moving forward. And first and foremost, we're going to talk about all these little shortcut rules for logarithms. We deal almost exclusively with natural logarithms, so if we ever have a common log, typically we're going to rewrite that. The first rule here is just the idea that if I have the natural log of a product, I can split that into two different natural logs. So here's our two natural logs if we add those together. So what that is telling us, and usually if we have time, we did this last period or fifth period, I'll have you do this. The natural log of 8, if we threw that into our calculator, is 2.019. Natural log of 8 could also be written as the natural log of 2 times 4. And what I usually have people do just to kind of prove this and recall this from last year, I actually have them throw this into the calculator because these should be equivalent expressions, and it's going to spit out the exact same thing. It's kind of like magic. All right, somehow magically that ends up being the exact same answer as the natural log of 8. So that's what that rule is. You also had a rule where if I'm taking the natural log of a quotient, I can do two natural logs, so the natural log of the numerator and the natural log of our denominator, if we subtracted those. So again, if we had the time, I would show you, but I then usually do like a 16 divided by 2, because that's still a natural log of 8, which is this. And if we throw this into our calculator, the natural log of 16 minus the natural log of 2 will magically turn into 2.018 as well. All right. Next one is largely the same rule, where you have a fraction, and you're going to do the natural log of the numerator minus the natural log of our denominator. But if you notice how this is a 0, that is because, and you'll want to have this, one of the things you're going to definitely want to know, the natural log of 1 gives us the value of 0. So when we graph the natural log curve here in a minute, that's got to cross the x-axis at 1. And then my personal favorite rule, if we have the natural log, oh boy, here we go. It's always this period. If we have the natural log of something raised to a power, can you guys see this good? I can make this a little bigger for you. We can take this power and move it out in front. So the one that I usually have people plug into the calculator, just so they're all natural log of 8s. If I wrote this as the natural log of 2 cubed, what that means is 3 ln of 2 would still give us the same exact value as the natural log of 8 gave us. All right. So you've seen all that. You probably dove into that, like why all this is true. Now you just need to know it. These we don't deal with a whole lot, so I wouldn't worry too much about these. Pretty much whenever we have a common log, we're going to rewrite that as a natural log. So these little rules you would have talked about quite a bit last year, not as quite a big of a deal this year. So the first thing we're going to do is just kind of refamiliarize ourselves with those rules. I want you to write these two expressions using a single natural log, using those properties that we just reviewed at the top. All right. So we'll kind of go through this first one. All that's going to tell us is we want to take this 2, make that the power of our x. So that becomes a natural log of x squared. And then we would still have plus the natural log of x plus 3. Then there's another property that says if I'm adding, which we are, 2 different natural logs, then we can condense that down into one natural log if we multiplied their composites. So we would do the natural log of x squared times x plus 3. If you want to distribute, feel free. If we had time, we probably would, but that's our answer. Okay, once we have a single natural log, we're moving along. 5 is similar, where we're going to take this 5, or not number 5, number 2 is similar, where we're going to take this 5, which is our coefficient. Because it's the coefficient, we can write it as the power of the composite. So we will write this as the natural log of x plus 1 to the 5th. This is the other rule that we haven't talked about of these two. If we're subtracting natural logs, which we are, we can condense that down into one natural log. If we divided their insides, and the first one has to be our numerator, the second one is our denominator. Maybe this one will simplify just to make sure we see what happens here. You would notice in your denominator here, you have the difference of squares that could be an x minus a 1 and then an x plus a 1. And then you had 5x plus 1s in the numerator. So the 1x plus 1 in our denominator would reduce down the numerator to 4 of them, and then we would still have an x minus 1 in our denominator. Okay. So you want to know those. That's certainly something that we're going to deal with. What's that? Oh, sorry. Yeah, you're right. It does look like a 9. It's a 4, I promise. Okay, next thing. Again, you want to know this stuff that at some point, maybe on a test, you might see like a standardized test. It's not something we're really going to deal with. Writing a common log into an exponential, it's not something that really pops up, but just a little refresher. What we do deal with is the natural log. So what I want you to do, if we had time again, we would expound on this a little bit, but it's an idea we deal with in chapter 5, so we're going to move along to just graphing this. So go to your graph. Definitely have the x value of 1 on the x-axis marked. And then the natural log curve should look like this. So it starts out increasing very quickly, goes through 1, but then he peters out a little bit, he has no stamina, and then he just kind of levels off. Now, he does increase forever. This doesn't have a horizontal asymptote. It looks like it may be leveling off towards something. It doesn't. It does increase forever. It just does it very, very, very slowly. So when we graph the natural log, the things I would look for is make sure you go through 1. And this is one that I would expect you to know without a calculator. Our AP test is half calculator, half non-calculator. This is one that they expect you to know without a calculator. So that's something you want to file away. And then we want to know that it's increasing the whole time, but it increases very, very slowly once we get past 1. Right? So that's our natural log curve. We're going to want to know that. All right, the number e. You also would have talked about the number e. So if we look up here again, the natural log of 2, so if I come over here to 2, that has a y value of 0.693. This is telling us if we come over here to the x value of 3, we have a y value of 1.098. The reason I say that is somewhere, didn't we have to hit the value of 1? Somewhere in here, we would have had to have hit the value of 1. We're constantly increasing, we hit a value of 1. Where we hit the value of 1 is at the number e. People get these mixed up a lot. The natural log of 1 is 0. You want to have that down pat. The natural log of e is 1. If I ask you for the natural log of 0, look at our graph. We're going to define domain and range here in a second. Good. It is undefined. We can only take the natural log of positive numbers. Okay, so no natural logs of zeros, no natural logs of negatives. Those are not defined in the domain of a natural log. Okay, so we want to keep all 3 of those straight. All right, now, so what's the number e exactly? Like, what is that even? Where does it come from? We decided to come up with a number that's called a letter. So we come down here. Now this looks weird. There we go. Hope this one comes in. All right, you can see on your paper what this says. Hopefully it'll come in. But the number e, you'll want to know this as well, is about 2.7-ish. So if you know pi is about 3.14, you want to know that e is approximately 2.7 for when we don't have a calculator in our hands. And then what the number e is, what you should see here, I don't know what, there it is, finally. So this formula here should look familiar to you. Last year, or some point, I don't know when you do it now in our Math 1, Math 2 sequence, this is the compounding interest formula. So you would have done banking problems if you invest a certain amount of money and you earn interest on that twice a year. How much money do you have over a certain period of time? That's our compounding interest formula. Very, very common formula, has a lot of different applications out there. So when we talked about that, that's what you would have used this for. So over time, as this started popping up with a bunch of different applications, what people notice, so let me show you this graph, because I want you to see this. Hopefully I haven't, nope.
Wait, is that the same thing as the PERT, PERT?
It is not the same thing as PERT. No. They're similar in terms of when you're going to compound your interest and all that stuff. Both of them come from investment problems. Say that again.
I said what's continuous.
One's like continuous compounding of interest, and then the one is every quarter, every month, so on and so forth.
Isn't PE to the RT like continuous?
What do you mean, like?
Like you learned two different things. One was like compounded every certain amount of time, and then one was like.
You might be right, because those ends are when we're going to be compounding it. So the ends would be every quarter, that's the end is going to be 4 or whatever. All right, so let me graph this real quick. So this is that formula that we had in our paper. And then we square this, or no, we don't. We raise this to the power of x. All right, so when we graph this, nothing terribly fancy about it. But where the number e eventually came from is people started kind of seeing and using this formula for different applications. Notice how as we go further and further and further right, notice how this thing appears to be leveling off. It looks like there's a ceiling there that it is approaching. If I now go to the second one, man, is this slow. And I graph the number e, so there's our e. That's what people then defined as the number e. It was the limit of that interest formula. So notice that is the ceiling that the e provides for that function as we go towards infinity. Okay? So that's where the number e evolved from, that's where it comes from, and we want to know that it's about 2.7. Okay? All right, next thing. So here's what I want you to do here. I want you to graph the natural log of x, just like we did on the front page. So do that real quick. Remember, there's one particular point you have to go through. Sketch it real quick. And then I want to see who's really good, who was paying attention really good yesterday. Once you have the natural log graph, I want you to graph its inverse also. All right, so let's see if you have your natural log graph correct, and then we'll give you a second to see if we can graph the inverse. We have to go through the point 1, 0. The natural log of 1 is 0. There's a vertical asymptote, which is your y-axis. So we get really, really close to the y-axis. We should never touch it. We can't take the natural log of anything other than positive numbers. And while we start increasing pretty quickly, we continue to increase, but eventually we do this very, very, very slowly. So this function is our natural log function. Now, with what we did yesterday, we should be able to graph the inverse of this. We should be able, if I have the original function, any original function, I should automatically be able to graph any inverse without knowing anything about what that graph would look like, other than knowing what we did yesterday. All right, so what we did yesterday, so we'll see if anybody did this correct. Remember how we talked about any function and its inverse will reflect around the line y equals x. And that comes from, it's part of the idea that when we write these as composites, that's what we always get. Oh my God. This doesn't act up except for 7th period. There we go. So if we ever write those as composites, those cancel, just giving us the x. So geometrically, what that means is our function and its inverse should always reflect around that line. So draw the reflection then real quick. See if we can do that. Because whatever the reflection is, by definition, has to be the inverse. So if I flip the black graph around the red graph, what would that look like when it's flipped upwards? there's one point you would have to go through. Okay, if we know the natural log of x for sure goes through the point 1 comma 0, wouldn't the inverse of the natural log of x have to go through 0, 1? Again, the whole idea of our inverse is x and the y's get flipped. So we would need to make sure you go through this point and look for that. As this guy approaches this vertical asymptote, never crossing the y-axis, the reflection should get really, really close to the x-axis without touching it. As the natural log curve flattens out, the inverse should be shooting up. So if you drew that, good. This has to be the inverse of this function. It would have to be. Anytime we reflect around the line y equals x, those are inverse functions. Okay? So then real quick, let me go back to my calculator. And what I'm now going to graph is the natural log of x again. And you can see what it looks like for sure. I'm not lying to you. So natural log of x. And I'm also going to graph that line that we reflected everything around, which is y equals x. Okay, so that's our natural log of x. It does go very, very close to the y-axis. It doesn't start at the -2, even though it kind of looks like it. And then here comes the line that we're going to reflect it around. We mentioned this yesterday, so the cat's out of the bag just a little bit. And you've seen it last year anyhow. But if I now graph this guy, not that guy, you got bad eyesight. If I now graph e to the x, notice how the e to the x is the reflection of the natural log of x around that line y equals x. So the inverse then of the natural log by definition has to be the exponential curve e to the x. All right. So when we go back to that, we can now change what we're calling this. Instead of calling this the inverse of the natural log, this really is, we'll call it g of x. That's our exponential curve. And the reason that's pretty powerful and useful is because of this over here. Change the colors. If I take a function and its inverse and write them as composites of each other, they cancel each other out, leaving us with just the inside. And if we do the exact opposite, the exact thing is going to happen. So the reason that is important is for what I have next underneath here. For this combination here, if I have the natural log of x and I replace the x with its inverse, and its inverse we've now said is e to the x, those have to cancel, leaving us with just the composite. So that's where this comes from. Same with the e to the x. Notice how the x is the exponent, so its composite is the exponent. If I get rid of the exponent and replace it with its inverse, which is the natural log of x, I'm creating these guys up here. Only option for me to come up with here is an x. That's what this one is saying. All right. If we go to the next thing, let's write these down. The value of the natural log of x. So if we look at the natural log of x here, starts out very quickly, but in reality, once we start going towards infinity, he grows very, very slowly. He works really hard. He likes plugging away, but he's just slow. When we look at e to the x, so e to the x, he starts out very slowly, just kind of getting warmed up, but once he gets past this value, he's going to start to increase very, very rapidly or quickly. All right. So that should also make sense. If they're inverses of each other, they're doing the opposite. Okay. All right, domain of natural log. Actually, write that real quick. Tell me what you think the domain is by just looking at that graph. A bunch of people in class, I'm gonna call them. Sedona. What do you think, Sedona? Where do we start at for the domain? Good. 0 to infinity with both parentheses is what she said. We get really, really, really close to 0. We just never hit it. And then what do you got for your range, Sedona? Good. Negative infinity to infinity. We do go to a positive infinity, but like we said, it's just really slowly. It's easy to think that there's maybe a horizontal asymptote right here, but there isn't. No. This goes to E.
Oh.
That's what's going to approach E. Okay. All right, the domain, we don't even really need to look at our graph, correct? We reviewed this a little bit yesterday. The domain better be the range of the natural log. So this better be negative infinity to infinity. And then the range better be 0 to infinity. Now we'll look at the graph here in a minute to confirm this, but those have to be true. And that's what you see here. You dealt with a lot of exponential functions back in Math 1 when you first would have been hinted at kind of a horizontal asymptote idea. So this gets really, really close to 0, but it would never actually touch the 0. Okay, and then obviously we go up forever. All right, these guys. Just to save some time, I'll give these. I do want you to write these down because I think it's good to see. And it's a pretty big idea and concept. So just write down what these values are. So if I asked you what is E, what was the first one? Negative what? Negative 1. Okay, so plug that in, or write that down. That's right, plug it in. This is just going to kind of show just how quickly and rapidly the exponential function is going to grow. If we do the next one, is E squared, right? So kind of big, right? 7, not too bad. Now, just going to 10, so not a big number whatsoever. So this is just a base of 2.7, getting raised to a power of 10, and we are already at 22,000 plus. So if you think about what that means, if I were to go to my graph right now on my calculator, and I look at this natural law or this exponential curve right here, if I want to see the black graph over here at the x value of 10, I better be up here at 22,026, whatever that was. Okay, so huge, an x value of only 10. And then the last one, if we do e to the 100, and a 100 is not a big number by any means in the grand scheme of things. Oops, a little too big there. Good luck even kind of defining what 2.6 to the 43rd power is and naming that. So huge, huge number, despite the fact our x is only a 100. All right, so huge, really, really big. So exponential growth functions grow incredibly fast. All right, so with that, let's pop back here. Some old algebra rules that you're going to want to know. We know these. If you multiply like terms, that's not yellow, they should get added, the exponents. You can see all of these where it makes sense because this is not formatting particularly good. It's really struggling today. So now let's do these. This is kind of the whole gist of all of this. This is the main thing we want to walk away with today. That if I take a natural log and an exponential function and I write them as composites, they cancel each other out. All we are left with is the inside term. So in this case, that can only give us an x. When we have an exponential function, the x is the exponent. So that's where we would have to put its inverse. So that's why when I get rid of this and I make the exponent the inverse, the natural log, these cancel, and that only leaves us with the 2. Right? When we get to number 7, just know that e to the x and a positive natural log of x, those are inverses of each other. Those are the ones that reflect around the line. The negative ln of x curve and e to the x would not reflect around that line. So the fact that I have this written right now, do not be the person who tries to tell me that those cancel and I end up with a negative x. We have to get the e raised directly to its inverse, which is a positive natural log. So what we do is we take what is basically a negative 1 right here. Using the rules we started the class with, we're going to make that our exponent so that we now have e to the natural log. And then now the composite is x to the negative 1.
Is that also the same thing as 1 over e to the natural log of x?
Say that one more time.
Is that also the same thing as 1 over e to the natural log of x?
No, because the only thing to the negative 1 power is the x. If the whole thing was to the negative 1 power, so this whole exponent of e was to the negative 1, that's then the whole thing getting put into my denominator. But the only thing we raise to the, yeah, the only thing we raise to then that power is the composite, the inside part. Okay. And then we'll actually do that here in a second in the sense of these are going to cancel. So it's the x that goes into our denominator if we want to make it a positive exponent. All right, number 8. Try number 8 real quick. See if we can do that one. There's a little bit of everything that we've done today. A couple different things going on here. All right. It's initially kind of the rules that we started with at the beginning, where if we have two different natural logs, we can condense that down into one, because our goal is to just get an e, that e raised to a single natural log, so we know they'll cancel. If we took that 2 and make it the power, that's kind of our first step. Make that the power of your x, and we still have plus the natural log of y. And then what we would hopefully see is in this exponent, we have two natural logs being added together now. So I can condense that down into one natural log if we multiplied their insides. So what we then do, or what we've now created, is the relationship that we want. We have the exponential function getting raised to its inverse function, which is a natural log. Those have to cancel, leaving us with just the composite of x squared y. Okay. All right, number 9. A couple different routes we could take. I think the way I'm going to do it, we're going to have to hurry up because we have 4 minutes, is I'm just going to do the, if I have one natural log, I can split it into 2 if I'm dividing by subtracting those. You could also bump this up as a negative exponent. That would work. But I like to also review that the natural log of 1 is a 0. So that's going to drop. So we really just get a negative 1 times the natural log of e cancels, x cubed. So our answer is just a negative x cubed. All right, number 10. Take the 3, make it the power of your x. Those guys cancel, and we're just going to get an x cubed. Okay. All right, moving along. We're going to do 2 of each of these. Again, you've seen this before. I think once you see 1 or 2, you're going to be like, yeah, this is easy. We have this. If we're going to solve exponential equations, it's just algebra. So whatever we do to one side, you got to do to the other. So if we look at this first one, the simplest one, if I'm trying to solve this for x, I need to get rid of the e. And that's kind of the whole point of what we just did. We now know how to get rid of the exponential function. We do that using natural logs. So, so we would take the natural, green. We would do the natural log of both sides. Try that again. So that these would cancel, and then x would just equal whatever the natural log of 72 is. Right. The ones to be careful of, if we go to 13, so jump to 13, 12 is very similar. The natural log of e to something would cancel. If that e has a coefficient in front of it, that's a problem. So this 40 can't be there. So our first order of business here is to get the e by itself. We want to divide that 40 over. Once the e is all by himself, now we can go ahead, take the natural log of it so that it'll go away. And then that's our answer. Okay? Yes, sir.
Can you go up to number 9?
Number 9? Yep.
Okay, how did you get negative x negative 3? Like, I get how you got negative x, but how did you get negative 3?
Oh, I don't know if it's supposed to be a negative 3, to be honest. I think I'm just trying to go too fast to make sure we finish. So it would have been natural log of 1 minus the natural log of e to the x cubed. So that would have canceled. And then the natural log of e is going to cancel. So it would have just been a negative x cubed. So I either was rushing or it was like just an accidental tick mark there. Okay, go to the last couple. If I give you a natural log equation, so I'm trying to solve this one for y, so we need to get rid of a natural log. So the way we get rid of natural logs then are e's. But keep in mind, in the exponential function, it's the exponent that is your variable. That's where the composite is at. So we don't multiply by e. That would not be correct vocabulary / correct mathematically. We basically raise those to the power of e. So these will cancel. We get y minus an 80, and then that would equal 5 to the t. And then add that over, and then that would be our answer. All right, we'll maybe do one or two of these tomorrow, just kind of refresh our memory. Not a big part. What we do tomorrow is much more important than this. This should all be review stuff that we're familiar with. Okay. Okay, we'll stop there.